Hi, I'm Marco Pizzoli. I'm a former PhD student at University of Rome La Sapienza, and this presentation is based on my PhD thesis, Experimental Data-Driven Reduced Order Modeling of Nonlinear Vertical Sloshing for Aeroelastic Analysis. This work was conducted under the supervision of Professor Franco Mastrodi as part of the SLOD project, whose partners are shown in this slide. As already mentioned, my PhD work was part of the European Horizon 2020 project SLOD, which stands for Sloshing Wind Dynamics. It aims to study the use of sloshing of fuel stored in wind tanks to reduce loads acting on aircraft structures. Fuel sloshing can manifest itself in many ways, but just to simplify the interpretation and understanding of this complex phenomenon, a classification based on the direction of motion imposed on the tank, which triggers sloshing, and its intensity was considered. In this way, two main types of sloshing were defined. The first, lateral sloshing, which occurs as a result of lateral rotational perturbation of the tank, and in particular, linearized dynamics can be identified involving free surface standing waves as shown in this animation. The second type of sloshing is the vertical one, which occurs as a result of a perturbation perpendicular to the free surface of the liquid. And in this video, we can see an example of mainly vertical sloshing, which also has a slightly rotational component. And such dynamics include complex nonlinear phenomena as Rayleigh-Taylor instabilities, turbulence, impacts. And the latter are responsible for the dissipation induced in the system, which affects the overall damping of the whole structure. And in my work, I have mainly focused on the study of the second type of sloshing, with the goal of identifying a nonlinear reduced order model to be later integrated into aeronautical application in order to evaluate the effect of vertical sloshing on the aeroelastic response. From a design and methodological point of view, an approach was used such that a combination of experimental campaigns and numerical modeling was used. In particular, the latter was based on the use of data measured precisely in the experiment. In fact, we speak of data-driven approach. And from a chronological point of view, the activity began with the identification of a reduced order model referred to as a bouncing ball through the use of experimental free response data provided by the University Politécnica de Madrid, one of the project partners. Subsequently, an experimental campaign was carried out in our laboratories in Sapienza to characterize the dissipative behavior associated with vertical sloshing by imposing harmonic motion of varying frequency and amplitude using a shaker. And the same experiment was used then to generate data for training a new nonlinear reduced order model based on neural networks. And this model was then experimentally validated by making a new layout, a new configuration referred to as sloshing beam, in which the tank used for training data generation is mounting on a cantilever beam. And finally, the validated ROM was integrated into the numerical models of two aeroelastic applications to evaluate the effects of sloshing on the aeroelastic response. The first reduced order model for vertical sloshing consists, as already anticipated, of a bouncing ball, which more properly represents a 1 degree of freedom system such that it emulates the impact mechanism that are generated between liquid and internal tank walls and that are responsible for the induced dissipation. The bouncing ball was identified on the basis of experimental free response data made available by the Universidad Politécnica de Madrid. And here we can see the experimental setup, and the identification was done through an optimization process aimed at obtaining a model capable of reproducing the same damping characteristics as those measured experimentally. And here we can observe comparisons in terms of acceleration and damping ratio, while a qualitative comparison between the experiment and the simulation with the bouncing ball is shown in this animation. And the advantage of this model is that it is very simple to use to perform direct simulations representing the tank plus liquid system. However, as shown by subsequent experimental campaigns, it is unable to faithfully reproduce dissipative behavior at frequencies other than the one of the free response with which it was identified. As a result, it was necessary to deepen the understanding of this phenomenon. To this end, experimental free response tests were neglected in favor of harmonic tests, since they allow to obtain a direct estimate of the energy that the liquid is capable of dissipating during vertical sloshing. And specifically, the setup presented here in this figure was implemented, in which a small box-shaped tank made with plexiglass was mounted on a shaker, this one, capable of imposing the desired vertical motion. And accelerometers and load cells were appropriately placed on the setup so as to measure both the imposed motion and the impact forces, thus the sloshing forces. And the size of the tank was chosen accordingly to the limitation of the shaker and to the need to trigger Rayleigh-Taylor instabilities, and so to get impacts. The purpose of the experiment is thus to characterize the energy dissipated by sloshing as the frequency and amplitude of the imposed motion change. The methodology adopted for this purpose consisted of performing a few very slow sine sweep tests represented in the figure by these iso acceleration curves in red, and this, on the other hand, is the law of the vertical motion imposed by the electromechanical shaker. And in this video, we can see an example of what happens inside the tank in the 1G test for the case with 50% filling level. This instead is the expression by which the work exchanged between liquid and shaker is calculated, and thus the energy dissipated by sloshing, so this one, where Fsz is precisely the force measured by the load cells, while U is the motion imposed, the vertical motion imposed by the shaker. And furthermore, the energy dissipated, so this work here, corresponds to the area enclosed within this hysteresis cycle obtained in the force displacement plane. By repeating this process of evaluating the dissipated energy for each of the points covered by the test performed, it was possible to obtain the maps representing the distribution of dissipated energy in the frequency and amplitude domains. And in addition, by introducing the dimensionless quantities of energy, displacement, and frequency, it was possible to obtain the same map, but representing the non-dimensional dissipated energy in here, which gives more insight into the nonlinearity of the dissipative behavior of vertical sloshing. highlighting the close dependence on both frequency and the amplitude of the motion. And the experiment was also repeated at different filling levels, in addition to the 50% fill level, representing this case already shown. And in particular, we have here the distributions of the energy for the 25% filling level case, and lastly, the one with the 75%. These additional tests were used to perform a sensitivity analysis as a function of the filling level, and specifically the region in which the non-dimensional dissipated energy is greater than or equal to the 85% of the maximum for each of the three filling levels are shown here in this map. And it can be seen that the case with 75%, so this one, turns out to be the one with the region having the larger extent. However, the most dissipated case is the one with 50% filling level, where the highest absolute values are found. In addition, this experimental campaign allowed us to characterize another important phenomenon. Specifically, the sloshing force can be decomposed into an inertial contribution, depending from the liquid mass, and a non-conservative contribution referred to as the dynamic sloshing force, which in turn, through a linearization process and considering a purely harmonic vertical motion, can be expressed as the sum of a contribution related to damping, and consequently to the dissipated energy that we characterized in previous slides, and an inertial contribution which is related to the so-called sloshing effective mass fraction, which was derived from experimental measurements and reported in the frequency and amplitude domain as shown in this map, in this figure. And this distribution tells us on a quantitative level that depending on the frequency and the amplitude of the motion, the mass of the liquid actively participating in sloshing can vary significantly. Okay, so because of the limitations of the bouncing ball mentioned previously, it was necessary to think of a new reduced order model that would be more representative of the phenomenon under consideration. And for this purpose, a black box modeling approach was adopted, which considers vertical sloshing as a model that receives as input the vertical motion imposed on the tank and returns as output the sloshing force, or the dynamic sloshing force. And the new reduced order model is constructed and built by training a neural network with experimental input and output data measured directly in the experiments carried out for the energy characterization of sloshing, so the one that we saw in the previous slides. Specifically, two additional variable frequency and amplitude harmonic experimental tests were performed, such as to follow the path here plotted in the figure in the frequency and amplitude domain, having a duration of 480 and 240 seconds respectively, where the first tests represent the training data sets, while the second is the validation dataset that we performed in order to get data for the training phase in order to avoid overfitting. And thanks to the sensors, it was possible to measure the input represented by the vertical velocity imposed on the tank by the electromechanical shaker, and the output represented by the dynamic sloshing force. And it is important to note also that this type of training data leads to the identification of a neural network valid only for a type of response having a main harmonic. This, however, does not turn out to be a problem for Aeroelastic problems, so applications, since the aerodynamics tends to filters out one dominant frequency and dump all the others. So this type of training process is consistent. Now, to create the reduced order model, the so-called external dynamic strategy was considered, which allows a nonlinear dynamical system to be identified with a model consisting of a nonlinear static approximator, represented in our case by a neural network having radial basis functions as activation functions, and a bank of input filters represented by delay lines, which are necessary to capture the dynamics of the process. And since the model is to be used to run simulation, to perform simulations, its structure must have a so-called parallel configuration. So this one is the one that we choose to construct the model, in which only the input, or at most even the estimated output, can pass through the delay lines. Whereas the other configuration, so the series parallel configuration, allows only to the measured output to be included into the system and to pass through the delay lines. But so we want to perform simulations, so we need a sort of closed loop if we want to integrate also the output as the estimated output. Okay, so in order to select the best performing model, a sensitivity analysis was performed on the model parameters by training different neural networks based model as the number of neurons or activation function and the number of delay lines varied. And this image shows the error trend on the training data associated with, so mostly associated with a model named nonlinear finite impulse response model, which involves only the use of the input and is passing through the delay lines to identify the dynamics of the process. And we also have 3 points here, square points, representing the other parallel configuration model, in particular the one that considers also the estimated output and is passing through the delay lines to identify the process. But it is clear that the NFIR model performs better here with respect to the other parallel configuration model, which also turns out to be less stable, and so it is preferable to use this one, the NFIR model. And in fact, the best performing models turn out to be this one, the one highlighted in here, which considers 70 delay lines and 35 neurons. And once converted to a Simulink block here, we can perform simulation to obtain the estimated dynamic sloshing force. And in this picture, we can see in red the estimated force compared to the experimental validation data force. And we can appreciate the capability of the network to well capture the nonlinear trend, so the nonlinear dynamics of vertical sloshing. The identified model was then subsequently validated by making and build up a new experimental setup in which the tank used for the data generation is placed at the end of a cantilever beam. And here on the left, we have highlighted the fact that on the, corresponding to this strip, horizontal strip, we have the frequency, or better, the non-dimensional frequency of the dominant mode of the cantilever beam. So we ensure the fact that the neural network that we identified works and can be used for this kind of problem. And in particular, by performing free response and seismic excitation tests at the base, it was possible to obtain the experimental data to evaluate the neural network performances in a fluid structure interaction problem. Practically, for the validation, a numerical model equivalent to the experimental one is first made, in which the identified neural network ideally replaces the tank with the liquid inside it, so as represented here. But this is done in Simulink, creating such a model, here represented, in which the modal formulation of the cantilever beam interacts with a closed loop logic here, with the reduced order model of vertical sloshing represented precisely by the neural network. So here we have the block representing the identified network. So the first type of experimental tests, as I mentioned, that we performed is the free response test. And in this video, we can see what happens inside the tank during the response. So there is a first phase with the very violent impacts and then the recomposition of the free surface. And on the right, on the other end, we have the time trends of the accelerations measured with the accelerometers appropriately placed on the beam, and in particular the comparison between the so-called frozen case on the left, in which the liquid is not free to move, and the case in which there is sloshing, so active sloshing on the right, is shown. So, and it is evident how the presence of vertical sloshing contributes to a significant increase in damping of the response compared here to the frozen case. And so by comparing the experimentally measured data with the numerical data obtained by simulating the numerical model containing the neural network, we obtain the results shown in the figure in terms of vertical acceleration of the tank and force exchanged at the interface between the tank and the beam. And recall that this experimental force was measured by load cells. And the curves are practically superimposed. And also by evaluating the damping coefficient by means of the logarithmic decay here, it can be further seen that the neural network is able to return approximately the same dissipative behavior as the liquid, as shown in this trend. Then the second type of test performed consists of seismic excitation imposed here at the root of the beam through the shaker, and three different excitation levels were selected at 0.1, 0.2 and 0.4 G, having a Gaussian power spectral density as represented in this figure on the right. And this is the trends in time, at least in a short window, representing the shaker excitation imposed. And the experimentally measured acceleration at the tank location is used to validate the behavior of the network for this loading case as well. So specifically, the results for each of the excitation levels are shown here, both in time on the left and in terms of power spectral density on the right, so in frequency. And the blue curves represent the sloshing experimental cases, while the dashed black ones represent the numerical evaluated frozen case that we reported, just to have an idea of which is the damping introduced by the sloshing into the response. And it can be seen specifically from the frequency results, so on the right, how even for this load case, the network is able to well estimate the sloshing induced damping, and in fact, at the first mode of vibration here, the peaks are at the same level approximately, and obviously below those of the numerically calculated frozen case. And on the right, we have also another evidence of the good behavior of the neural network, because we reported the estimated damping ratio, and we have that the 3 parameters estimated are in good accordance with the experimental ones. So the network behaves well also in the seismic case. However, real-world applications involve the use of tanks with different dimensions than the ones of the tank used to generate the training data, so the box-shaped tank. And therefore, in order to study the effects of sloshing in aeronautical problems, it was necessary to introduce and define a scaling law in order to use the identified neural network-based ROM as a surrogate model for vertical sloshing for different tanks. And to this end, a dimensional analysis was conducted to highlight the most important non-dimensional groups on which the non-dimensional dissipated energy, or equivalently the dynamic sloshing force shown here in the figure, depends. And here, for example, we have the most important groups, which are the operative conditions dependent groups, like frequency, displacement, so the amplitude of the motion, and velocity, which corresponds to the fluid number, and the filling level, and the parameters related to the fluid characteristics, as bond number related to surface tension, and Reynolds number related to viscosity. And so by remapping this quantity, so the energy or the dynamic sloshing force, on the velocity this time and frequency, we obtain this map, and this helps us to introduce the scaling law that we defined, that assumes that the dissipated energy depends exclusively on these two operational parameters, the velocity and the frequency, with the assumption that the parameters related to the physical characteristics of the fluid, so bond and Reynolds, play a secondary role. And however, this assumption is partially supported by numerical studies presented in some papers published by partners in the SLOD project. And then, so the scaling law is defined in this way. So by the satisfaction, so of the similarity condition on the two operational parameters, so the frequency and velocity, and the non-dimensional dissipated energy. So by respecting the similarity conditions on these three parameters, we can use the scaling law to use and to integrate the neural network also in that kind of problems, which includes tanks with different dimension than those of the tanks used for the training phase. The first application studied consists of a model of a prototype commercial wing having 8 tanks of different sizes within it. The numerical modeling was done in Simulink again, realizing an hybrid model in which a linear differential problem here interfaces with a nonlinear data-driven problem. And specifically, this block represents the modal formulation of the structural dynamics based on the finite element model of the wing, here represented, while this block implements the unsteady aerodynamics model with the DLM, so the doublet lattice method. And on the right, we can see the stability scenario of the linear differential problem, so the aeroelastic system, and also highlighted the flutter speed at 319.3 meters per second. So above this velocity, the system is unstable. And in contrast, the last block here represents the nonlinear dynamics of vertical sloshing, where the scaling law introduced into the previous slide is implemented for each one of the 8 neural networks to represent the vertical sloshing in each one of the wing tanks. So now we go on to see the effects of vertical sloshing on the aeroelastic response of the system to a Gust having a classical 1 minus cosine profile. So the first response analysis is conducted under subcritical conditions, specifically at a flight speed of 266 meters per second. In this condition, the frozen case is compared again with the sloshing case, in which the neural networks are active. And both the system are stable, as we can see from this graph here, in which we can see the trends of the acceleration at the wing tips. And it's clear that the sloshing fuel case presents a more dampened response. And so, although the aerodynamic damping is high in this condition, the role of sloshing is evident. And this is due to the presence of liquid impacting inside the tanks. And here, in these two GIFs, we can appreciate the animation of the response of the system, and where these 8 balls represents the motion of the liquid COG estimated from the sloshing forces. In the second response analysis, the velocity is increased up to 315 meters per second, again under subcritical condition, but closer to the stability margin, so closer to the flutter speed. And also in this case, both models, so frozen and sloshing, are stable, as can also be seen from these trends of the tip acceleration, and from the 2 animation showing the response of the wing. In this case, the aerodynamic damping is lower than the previous case, and thus the damping induced by the vertical sloshing on the response is even more evident, as we can see from here. Finally, the third and last response analysis is conducted instead under post-critical condition at a velocity of 321 meters per second. And in this case, the frozen model is unstable, as we expect, but sloshing succeeds in introducing enough damping to favor the onset of a limit cycle oscillation. And this is evident from the acceleration plots and from the 2 animation, in which we can see from the animation on the left that the response grows indefinitely, while the sloshing case response presents an oscillatory behavior that remains limited into a certain range. And by repeating this analysis for different velocities, this bifurcation diagram was obtained, in which we see that the stability margin turns out to be backward from what we expected. So from the velocity, the flutter velocity of the frozen case. In the next slides, we will see the cause of this phenomenon. In particular, it is also possible to make an a priori estimate of the bifurcation diagram, reasoning from the energetic point of view, and specifically assuming that the aeroelastic response is solely determined by the critical mode corresponding to this unstable branch shown in this stability scenario of the system. The energy exchanged between structure and aerodynamics as the flow amplitude and velocity change can be calculated and reported here in this map on the left. And the blue part represents the region where aerodynamics subtract energy from the structure. So the aerodynamics here induces damping, while the red part is the region where aerodynamics gives energy, so provides energy to the structure. And similarly, an energy map associated with vertical sloshing only can be identified by just summing the contribution of each of the tanks derived by considering the experimentally characterized energy map. And so the final map for vertical sloshing is this one, that is all in blue, since this phenomenon is just capable to subtract energy from the structure, so to induce dissipation. And by summing these two maps, we obtain the map here in the center, to which we superimpose this bifurcation diagram, that is the one shown in the previous slide, so the one obtained from the Gust responses. And the line highlighted here in yellow, namely the zero energy line, represents the locus of the points where there is the perfect balance between what is dissipated and what aerodynamics provide to the structure. And this should coincide with the bifurcation diagram obtained from the Gust responses. This is not the case here, although this happens if the contribution of the sloshing effective mass fraction is also considered in the formulation. In fact, here we have the flutter velocity trend as the filling level changes in the frozen case, here reported in the center, while this is the already shown experimentally characterized sloshing effective mass fraction map. So the mass fraction is denoted as beta, and here we have its distribution in amplitude and frequency. And by selecting a low amplitude average beta value and including it into the problem, an inertial effect is created here that changes the stability margin. So the flutter velocity is lowered with respect to the frozen fuel without mass correction model. And this results, in terms of energy, in obtaining a map in which the zero energy line, so the yellow line, is superimposed on the bifurcation diagram found from the Gust response analysis, here, as we can see from this map. So the identified reducer order model can faithfully reproduce the behavior of vertical sloshing even when integrated into a complex aeroelastic system as the prototype commercial wing. Now, the second and final aeroelastic application consists of a flexible aircraft model in which both aeroelasticity and flight dynamics are involved. This model, also referred to as body freedom flutter, has the characteristic of going into dynamic instability, so flutter as a result of the coupling between rigid body dynamics and aeroelasticity. Also considered in this application is the combined effect of nonlinear vertical sloshing, modeled with the neural network-based ROM, and linearized lateral sloshing, which is represented by means of equivalent mechanical models already used in previous work, as well as in my master degree thesis. The only note about this is that the equivalent mechanical model introduce added states in the formulation, added states representing the linearized sloshing dynamics. And the assumption made is that we can consider the combined effect of the two dynamics of sloshing by simply summing the forces estimated from the respective reduced order model. One of the test cases studied is the one shown here in the figure, in which two parallelepiped tanks were placed symmetrically under the wings of the aircraft. Also, in this application, it was necessary to use the introduced scaling law in order to fit the neural networks to the dimensions of the two tanks. And here on the right, we have the stability scenario of the aeroelastic system, and it can be seen that the linear sloshing through its added states interacts with the other dynamics of the aircraft by altering the stability margins in a clear way. In fact, we goes from the frozen fuel model that presents the instability with the short period mode to the model with the lateral sloshing that presents a totally different scenario with a critical bending torsional mode. Lastly, we performed also a gas response analysis, and this slide shows what happens in post-critical conditions. So in particular, we compared four models: frozen fuel model, the model with lateral sloshing, the model with vertical sloshing only, and finally the model which considers both lateral and vertical sloshing. And it's clear again which is the impact of vertical sloshing in the response. In fact, we have that it induced a damping in the response that leads to the onset of limit cycle oscillation. And so this happens both for the first dry vibration mode, so for the structural dynamics, that for the rigid body dynamics, because here we have the local angle of attack trends. And so this confirms the very important effects of vertical sloshing in loads elevation. So this could be very important in the design phase of the loads acting of an aircraft. So this concluding slide resumes all my work, so the work done during my Ph.D. and following this timeline, starting from the identification of the bone symbol model to the harmonic tests done for the characterization of the sloshing behavior, and to the collection of the training data for the identification of the neural network, which was validated experimentally with the sloshing beam and then successfully applied to these two aeroelastic application thanks to the introduction of the scaling law. So in the next slide, we will see the future developments regarding vertical sloshing. This slide shows the future developments that we identified at the end of my PhD activity. In particular, the first is the application of the same modeling approach for the numerical model of the Airbus XRF-1 to study the effects of sloshing on stability and aeroelastic response of the free-flying aircraft. And the second point is the identification of a new reduced order model based on neural networks that consider also changes in the feeling level. In fact, the neural network based ROM that we identified and we presented was trained with the experimental data collected with 50% feeling level. So there is the need of obtain a more complete and general model that also takes into account changes in the feeling level. And we have some preliminary results on this already, and we obtain them just training a new model by considering an additional input in a training phase, and so we consider the feeling level as an additional input in the model. The last point was the experimental campaign to characterize the energy dissipated by sloshing again, but this time by considering also the effect of the tank rotation combined to the purely vertical motion to assess some possible differences in energy map. And we performed this experimental campaign, and we also published this work at the IAA conference of 2023, and we showed that the tank rotation contribution is negligible in terms of energy dissipation with respect to that of the purely vertical motion. So in this very final slide, I just collected all the publication done with my research group and some partners of Slow-D project, and I collected them in journal papers and conference papers. So I'm very happy with this. It was very successful research activity, I can say. And that's all, and I want to thank you for the attention. Bye.